Okay, so okay, so we see one by one for Xin Zhongsing. Does it matter? You still can attend class, but and then for the list, Amy will reply you on Monday. Okay, so yeah, then we see how. Yeah, Miss, once your name already in, I will update the attendance. Yeah, for the previous classes. Okay. Okay. Each group, Wong Hong Jack. You belong to each group. Either okay, let me know. Yeah. Same. Jiu Yu Hua, let me know each group you belong to. It's okay, I can check also. Wong Hong Jack.
I belong to deep learning.
No, you tell me. No, here got 3 groups only here in the list. Okay. We don't have the deep learning, but here got PT. But it's okay, I check one by one, don't worry. Okay, easy, very easy. Yeah. Okay, Jiu Yu Hua, done. Yeah. Okay,
Yeah.
Yeah, okay, done. Okay.
Thank you.
Okay, thank you. Okay. Okay, so now we see if no question for the previous class, so we see the second year. So remember power is where we reject the null hypothesis. Maybe the null is false. It's something good. Okay. So we are here power. Okay. So reject the null hypothesis, but the null is false. Therefore, it's something good. Okay. So therefore, we try to increase the power. Okay. So how to increase the power? We have 3 important factors. First is effect size. Okay, the effect size larger, therefore it's easier for us to reject the null hypothesis. Okay. So now we see alpha. Okay, so alpha, with alpha is smaller, therefore more difficult for us to reject the null hypothesis. Okay, so normally alpha is 5%. Okay, so we see alpha is a significant level. Okay, so it's okay. I can tell you now. Yeah. Okay. And some, of course, as usual, some still remember, some maybe cannot remember. Okay, I'll show you alpha. Yeah. So alpha will link to the critical value. Yeah. Okay. So alpha, let's say alpha is 5%. What will happen? Yeah. So when alpha is 5%, okay. Okay. So this curve is very, very important for us. Yeah, this is a normal distribution curve. Okay, we see this now. Yeah. The curve looks like this. Actually, it's recall a quick revision here for what you learned in statistics. You know, the prerequisite module. Okay. Okay. So the total area under the curve is 1, therefore it's 100%. Okay. So now we see the let's say we want to do 2-tail test. Yeah. Okay. Again, this is only the quick revision. Okay. So you want to do 2-tail test. Yeah. Okay. Therefore, the mu is equals to to 0. Now let's say okay 8. Can you see? This difference between what they call this is our 2-tail test because it's equals and not equals to. It's a same symbol like this. Yeah. Therefore, will be the 1-tail test. Now we see for 2-tail test. Right. So therefore, you see got 2 tail. Here, left and the right side got 2. Okay. It's a name 2 tails come from. Okay. And then we see alpha. Don't worry, this one must link to alpha. Okay. So alpha can be 1%, can be 5%, can be 10%. This is a normal practice. Okay. Okay. So we see the 5% case. Yeah. Therefore, it will be easier for us to compare, because 5% meaning that later can reduce to 1% or increase to 10%. Yeah, for our discussion. Right. Let's say 5%. Therefore, two-tail, meaning that this 5% actually representing the two-tail. They share among the two-tail, 5% over 2. You get 2.5%. Okay, so 2.5% for each tail. Okay, this two-tail. Okay, if no problem. Okay, if no question, now we see next. Yeah. So then this one I mentioned yesterday, this one must be 1.96. Here is negative 1.96. Because this is Z. Z is standardized distribution. Standardized normal distribution. Okay. So when you put X can be anything, can be any variable. But we standardize it, become Z. Okay. So we see next, yeah. Okay. Therefore, Z here, therefore here must be 0. You cannot put any other value. Yeah. Okay. Okay. Also mention one thing that you supposed learn before, like this. Yeah. So some of you maybe still can recall back. Hopefully, yeah. Remember this thing? Yeah. Okay. So when here you put Z, here must be 0. Meaning that 0 is the mean under the standardized normal distribution. Yeah, but the variance is 1. Yeah. If here you put X, N means normal. This is normal. This is normal distribution. This is standardized normal distribution. Okay. Normal distribution, standardized normal distribution. Here is mu. Therefore, can be any value. Because S can be any variable. Yeah. Example can be your height, can be your weight in kilogram, can be the distance between you, your house to campus, therefore kilometer, and so on and so forth. Okay. So the mu can be any value, but we standardize it, so become the Z. Therefore Z, the mu must be 0. How to convert X to Z? We use this formula. Okay, you can convert X to Z using this formula. Okay, so you suppose also familiar with this one. In this one, you in degree you normally do manual calculation. Normally, yeah. Okay. If your degree is from, I think IT also learn, yeah, correct. IT from APU, they also learn statistics. Some program, not all, maybe not all. Right? But business, economic, accounting, confirm. They also confirm. Normally, they learn this. Okay. So, if no question, so we come back
I ask you about the standard this Z score. Sometimes the sigma on the denominator, the sigma is divided by the n square root. What is the difference between?
Okay, good question. Okay, very good question. Yeah. Okay, the Z can be this. This is for the normal. Yeah. So and then you are right. So sometimes we use this. Yeah, Z x bar minus mu over sigma over square root of n. Yeah. Okay. So very good question. Your question is quite advanced. Yeah. But it's okay. Don't worry. I still can answer you. Okay. So for this one is the normal. You use this when you learn the normal distribution. Yeah. When you use this when you learn the sampling. Okay. The sampling distribution. Okay. So you see here, here is X, here is X bar. X is the normal distribution, but X bar is the sampling distribution. Okay. So and then sigma is the standard deviation. Sigma over square root of n is the standard error. So meaning that okay. No problem. I can show you. Yeah. This is the module that learned by IT student, in year 2. Yeah. Okay. Okay. So meaning that we, for the normal distribution, you only take one respondent. Let's say one person or one object. Yeah. But for under the sampling distribution, your n must be more than 1, can be 2 and above. From there, you compute the standard error and so on and so forth. Yeah. So this standard error. So this example is okay. You want to know? No problem. This is quick example to discuss the sampling distribution. Okay, we see this now. Yeah. A class 5 students, your test mark like this. Okay, therefore n is 5. Remember, n is the population mean. N is the population size. Population mean mu is 6. Okay, and population size is 5. Okay, mu is 6. Remember, under the sampling distribution, every time you must take a sample of more than 1. Can be 2, 3, 4, and so on and so forth. Okay. So this is the possible samples. Example, you take student 1 and 2, at least. Okay. If you choose student 1 and 2, you will get 3 and 5. You see the first column and the third column first. Okay. And then student 1 and 3, you get 3, 6. This is how you get the sample, the first and the third column. Okay, the first and third column. Okay. If no question, now you see we can compute the sample mean. We take 3 plus 5 over 2, we get 4. We call it sample mean. This sample mean is also the sample mean for not here. Let's correct this one. This is a x bar is a sample mean. Okay, x bar is sample mean. And then yeah. So because we got 10 samples, yeah, 10 samples actually from here. Some may learn this in high school. 5C2. Okay, so C is combination. Because here got 5 students. Each time you take 2 students. Therefore 5C2. You can use calculator. 5C2 is 10. Okay, any question? Yes. Okay, so if no, now we see next. Yeah. Okay. So yeah, we are here. Okay. So 5C2 is 10. Therefore, we get 10 samples. From each sample, we can compute the sample mean. Yeah, let's say you see here 4, 4.5, and so on and so forth. Okay. After that, okay, homework. That's homework. Okay, quiz. For quiz. Right. Now you try to do some calculation. You take 4. You find the mean for the sample mean. Again, you find the mean for the sample mean. Okay, how? Yeah. I give you the method. You do calculation now. Okay. You find the mean for sample mean. So you take 4 plus 4.5, everything. You see, these 5 numbers, here 5 numbers. These the values in the second and the fourth column. The second and the fourth column. Yeah. So you sum together, and then you divide it by 10. Because 10 samples. Then you tell me what is the answer. Now, yeah.
This 6 is the same as the population mean.
Yes, very good. Yeah, very good. Yeah, must be 6. Okay. This is based on the theorem. Yeah. So the mu must be equals to the mu for x bar. The mu is calculated based on the original value. This is mu. Okay. The mu for x bar, we call it mean for the sample mean. Or the, it's okay, yeah, mean for the sample mean. Therefore, we compute this value based on the sample mean. From sample mean, you compute the mean. We call it mean for the sample mean. By theorem, these two must be the same. Therefore, it's 6. Okay. Okay, this is first. Second thing, that's why you see these two are the same. That's why we can see this formula. Here x bar, same thing. Same, yeah, okay. But the standard deviation different. Yeah, under the normal distribution, we only take the sigma. But under the sampling distribution, we use the standard error. Because we should also consider the difference in the sampling. Okay, we should consider also the difference in the sampling. Okay, so let's say like this. Yeah, you see, I take the first sample, you take the second sample. Yeah, so sometimes maybe like this. Can I say the sample 3 like this? Maybe like this. Therefore, we should consider the variation between the samples. Sigma standard deviation only consider the difference among the respondents, the elements. But now standard error is equals to standard deviation over square root of n. Therefore, we also consider the variation among the samples. Even same population, this diagram showing that even same population, but for me, I take this sample x1, you take x2. Other literature take x3. Therefore, the sample will be different. And then from here, we compute the x bar 1, x bar 2, and so on and so forth, x bar 3. All can be different. Therefore, we should consider the variation, the differences. Before we use this formula, the standard error. Okay? So it means we use the standard error under the sampling distribution. Okay? So this is basic normal distribution. This is sampling distribution. There's a difference between these two. Okay. Okay. Any question? Yes. Yeah. Thank you.
Let's say if I get, let's say if I send out the questionnaire and get the respondent to fill up the questionnaire. So which Jack score should I use, with the standard error or with the standard deviation one?
Okay. So actually, if you take a sample, confirm cannot be 1, kind of. Let's say you take 50. The respondent, no, master maybe should be more. Let's say 300. Okay. Let's say 300. You got 300. Your sample size is 300 in your study. So therefore, you must use the sampling distribution. Okay. So you should use the sampling distribution and not the normal. So of course, normal is important for us to understand the sampling distribution. It's a basic. Okay.
Okay, sir. Thank you.
Okay. No problem. Now we see. Now we are here. Yeah. Before that. So for today, the break time will be follow the schedule. Yeah, means 3 to 3:30. Yeah. Okay. 3 to 3:30 and then 5 to 5:30. Okay. So therefore, this section end at 3. Then 3:30 continue like that. Okay. So means today will be okay. That's it. So today will be 1 and then plus 1.5. Yeah, and then plus 1.5. Okay. 3 sections. The first section 1 hour, second 1.5 hour, third 1.5 hour. Okay. So like that. Okay. So okay. Now you see this. Okay. So now we come back here to see the alpha. Yeah. Okay. Again, this thing is very basic, but it's very important. Yeah. At least in the next few chapters. Okay. So anyhow, Okay, statistics we cannot run away from the normal distribution. We see. Yeah, next. Okay. So therefore Z here must be 0. And then we know that the total area under the curve must be 1. And we see a bit more now. We see the right side, the right here. Yeah. So the right here is 2.5. Therefore, the purple color, the larger area must be 97.5%. Okay.
Should be 95, right, sir?
Sorry?
Should be 95, right?
No, 97.5. Because until the end, until negative infinity.
I mean, one side is 2.5, the other side 2.5 is 5 already. So
No,
remaining is...
97.5 is not the middle, but it's until the negative infinity.
Oh, okay, understood.
Okay, until negative infinity. Okay. So next we see. Now we see how to use this percentage to find 1.96. Okay. How to use the percentage to find 1.96 using Excel. Yeah. So normal inverse. Okay. Normal inverse probability 0.975. Okay, the function is normal inverse. NIV means inverse. Okay. 0.975 is from here, 37.5%. Right. The mean must be 0. Because now we are doing Z. Okay, see Z. Mean is this value. Mean, 0 is the mean. Okay. And then the standard deviation must be 1. Because it's Z. We enter, we get 1.96. Okay. Okay, any questions so far?
No, yeah, I think last time we got this video from the Bukusi here.
Yes.
Yes.
Yeah. Yes, correct. So, I mean, for the PVC, of course, we study this manually, using table, yeah. So using table, so okay, using the normal distribution, your table, okay. So of course, I still have the table. Of course, now you are data scientist, so you learn the basic first, yeah. Then we come to the basic. I mean, in the real life, of course, we use software, yeah. Okay. So okay. So I got a T, I got a T. It's okay. Can you see? This is T. Is like this. Okay. I'm sure we can find this manually, but now we focus more on the software. Okay. So we see next. Yeah. So this time we get 1.96. Therefore 5%, 1.96. Okay. I mean for two tail. For two tail. Okay. Now we change to 10%. Yeah. Now we change to 10%. Yeah. So 10% are still two tail, but now 10%. 10%. Okay, I use a different diagram. So 10%, therefore here is 5%. Because we're still using two tail. You needed everything all the same with the previous diagram, but only alpha change. Yeah, only alpha change from 5% to 10%. Okay. So therefore we see this. Okay, I change color. Therefore we see this black color. Yeah, the black color will be 95%. Okay, just now 97.5. Now 95%. Okay, now 95%. Therefore, we can compute this this value. We can compute this value. We will get 1.645. Okay, we do it now using Excel. Yeah. Okay. Same function like just now. INV, yeah. But now we only change the property. The rest all same. Yeah. So 0.95, and then 0, and then 1. Okay, you will get 1.645. Okay, yeah. You see all the same, yeah, Z and then 0. Okay, so if no question, now we see next. Yeah. Where? Okay, okay. Okay, okay, okay. Yeah. Okay. So if no problem, now we see next. Yeah. Okay. So now we see different alpha. We get different critical value. You see. Okay. Yeah. It's good also for you. You learn how to use the table to find the value. Therefore, we see also the value, the z value. Yeah. The z value from table. Yeah. Technically, we call this critical value. Okay. You can call it table value, not wrong. But technically, we call it critical value. Yeah. Okay. Means to answer exam, you can use reject value from table. But for your capstone, you must use critical value. Okay. This is the professional term. Okay. And then z value from formula. Yeah. So the formula we call this. You can call it z score. Is correct. But technically, again, technically you call this test statistics. Okay. Yeah. Statistics. Yeah. Okay. Okay. So formula means the two formula I show you just now. Yeah. These two. Yeah. Either one. I mean, all these two formulas. The z value that we get is the test statistics. Okay. Okay. If no question, now we see next. Yeah. So now we combine these two. Yeah, we combine these two diagrams into one. Yeah. So and then I only focus on this area. Okay. I zoom it. Okay. The rest not important. Okay. You see now. Yeah. So therefore the diagram will be something like this. You can see because I zoom it. Okay. So 1.645, and then here is 1.96. Okay, in Z. Okay, so and then we see 1.96. Yeah, 1.96. How we get 1.96? Yeah, from the alpha equals to 5%. 1.645 is from the alpha equals to 10%. Okay. Okay. Until here, you're supposed to learn it in other module, but the next maybe not. Maybe not. Okay. So we see a bit more now. Yeah. Okay. So when you suppose somehow most of you should learn this in high school or degree. When we use critical value approach, okay, we can use this method to help us to determine either we should reject or not to reject the null hypothesis. Okay. Under this approach, when the test statistics, yeah, is larger than the critical value, we must reject the null hypothesis. Okay. When the critical value is smaller, the test statistics is larger, then we must reject the null hypothesis. Okay. So next. Okay. Now we see, therefore, whenever the test statistics is larger, means we are happy because we can reject the null hypothesis. Okay. Now we see three cases. Okay. Let's say it's here. Okay, this is the test statistics. Let's say test. Okay, test statistics is 2.41. Yeah. Okay. Therefore, you see the purple color. I mean, this 2.41 is from the formula. Therefore, it's from your data. You see the difference between the test statistics and the critical value. Test statistics is from your data. Therefore, different capstone, different test statistics. But all of us must use this value in the whenever alpha is 5%, and then for truth here, for the Z. You can see this is from the theorem, from the formula, from the theorem, because statistician also use formula, of course different formula to develop the what they call the table. The table we mentioned just now. Okay. So means all of us will use this value 1.96, 1.645. But different capstone, you will get different test statistics. Okay. Let's say you get 2.41. What is the implication? 2.41. Yeah. So this one, it's okay. I think I can do like this. Yeah. No, it's okay. This is okay. 2.41. Yeah. 2.41 is the test statistics. Okay. So let's say 5%. Yeah, and then 10%. Yeah. Okay. What is the critical value? The critical value is 1.96. Okay. Here is 1.645. Okay. Okay. So you will see three cases. First one is 2.41. Yeah. So therefore, it's quite large. Yeah, 2.41. So we needed 2.41 is larger than 1.96, also larger than 1.645. Remember, number on the right side must be larger. Okay, use this logic to understand this diagram. So 2.41 is larger than 1.96, also larger than 1.645. Therefore, we reject the null hypothesis under these two cases. You see, we reject the null hypothesis because 2.41 is larger than these two numbers. You see the theorem here? Yeah. Okay, we call this golden rule. Okay, golden rule. So whenever the critical value is smaller, test statistics is larger, we reject the null hypothesis. Okay. So therefore, we reject the null hypothesis. Okay. Okay. Any question? Yes.
Oh, sorry,
okay.
question. I have a question.
Yeah,
Because currently you are using the critical value to compare, but in our statistic that we are learning actually using the percentage things to compare with the critical value. Also the same, is it?
Wait, what do you mean by percentage?
For example, 1.645 convert to percentage using the table, the CFIR table.
No. I think most probably you confused with another issue. Next, this is what we are going to discuss in Java. Yeah, don't worry, I know what you mean. So actually, you are saying the p-value, right?
Yes.
Okay. So p-value we see in the short while after this. Yeah. So compare p-value with the alpha. So alpha 5%. Yeah. P-value let's say 2.67%. Therefore smaller. Therefore we reject the null hypothesis. Yeah. So we got two methods. Okay. Yeah. So we see this after this today. I think suppose after break. Okay, we see how. Yeah. So now we reject the null hypothesis because test statistics is larger than 1.96, also larger than 1.645. Now we see second case. Let's say here. Yeah. Let's say 1.226. Okay. 1.26. Okay, so therefore 1.26 is quite small, smaller than 1.645, also smaller than 1.96. Therefore, we cannot reject null hypothesis. Okay, so under both condition, yeah. So 1.26, yeah. So not reject, not able. Okay, not reject. It's okay. This is simple English. Okay, so we cannot reject the null hypothesis. Okay, yeah. Okay. This is a little bit technical also. Yeah. I never say wrong, but in general, we never say not say never. We seldom say accept the null hypothesis. Okay. So we seldom say accept the null hypothesis. Okay. So we say either reject or not to reject the null hypothesis. Okay. So like this. Okay. So if no question, now we see next. Yeah. Okay. So one more case, let's say here, in between. Yeah, can I see? Meaning that if the test statistics is very small, it's easy. Very large, also easy. Let's say in between. Example 1.82. Yeah, 1.82. Therefore, 1.82 meaning that it's a bit different, a bit special. Means we can reject the null hypothesis when alpha is 10%. Because 1.82 is larger than 1.645. Okay, so therefore 10% we can reject. Yeah, here, yeah. So 1.82. Okay, so here you reject. Okay, when the alpha is 10%, you reject the null hypothesis. But when the alpha is 5%, we cannot reject the null hypothesis because 1.82 is smaller than 1.96. Okay, so this is the technical part. Okay, any question? Yes. Therefore, 2.41 easy, 1.26 easy, 1.82 is important for us to discuss an idea. Okay.
So, sir, later you will teach about the beta power in this example, right? It's just
no, we are doing beta not too important. We see alpha and the power. This one actually linked to power. Remember, linked to power. No, not here. This one linked to power. Can I see? We are doing the second point. The power. Okay. Okay. Now, good question. So now it's a time for me to answer your question. Yeah. So therefore, we of course link to this one. Okay. Meaning that in conclusion, when the alpha is large, when the alpha is large, it's easy for us to reject the null hypothesis. When the alpha is small, yeah, it's not easy for us to reject the null hypothesis. Therefore, 10% drop will drop to 5%. Means when the alpha drop, it's not easy for us to reject the null hypothesis. Therefore, the power also drop. This conclusion in the slide. Okay. Can you see here? Yeah. So alpha smaller, therefore the power drop. Example 1% even more difficult for us to reject the null hypothesis. Okay. This is the second point. Yeah. So therefore the alpha can affect the power. Yeah. So for your capstone, depends on your supervisor, but normally 5%. Normally.
So power is considered like a linearly proportional to alpha? Or
Again?
so power is something considered like a linearly proportional to the alpha?
Okay, good question. It's proportional but not linear. You can see diagram is not linear. You can see? Yeah, it's not linear.
Ah, okay.
Okay. The effect, notice here, they didn't mention power. Power is fixed, but it's not linear.
Yesterday, yeah, we didn't touch much on this graph. Yeah, okay.
Now this one we're not going to discuss. We discussed this one, yeah, the previous one, yeah, this one.
Yeah, yeah, only this one, yeah.
Okay. So we continue. Yeah.
Okay.
Okay. So if no question, now we see the sample size. Okay. So sample size. Okay. I think we come back at 320 because sample size also take quite some time. Okay. So 320. Yeah. Okay. We come back at 320. Okay. So still a break 30 minutes. Okay. But bring a bit earlier because I need more time to discuss the sample size. Okay.
Okay.
Okay, thank you. Okay, so we still use the same button to what they call to connect to join the class. So see you at 3:20. Okay, 3:20. Try okay. So 3:20. Okay.
Okay.
So thank you. See you in a short while.